Ultimately, our goal is to try to graph a polynomial function just being given the equation, like the ones that were given here. Now, we already know some elements of the features of polynomial functions. We could find the y-intercept by plugging in 0. We could look at the leading coefficient, determine based on the highest exponent and the positive and negative sign whether it's disco or whether it's a touchdown graph of some sort. We could figure out whether it's going up on the left and down on the right, or vice versa, or both sides down in that Australian rules football style, all based on that leading coefficient test. And although we've explored the zeros a little bit, we haven't tried to just start from scratch and try to find the zeros. Generally speaking, we've either been given the zeros and asked to write a polynomial function, or we've been given a zero and asked to find the rest. So here, we want to start to develop a process for trying to find the zeros of a polynomial function just given the function itself. And so, for starters, we know how many zeros we have to find based on the highest exponent of the function. So if the highest exponent is 3, then that means it's going to have 3 zeros. If the highest exponent is 4, that means it's going to have 4 zeros. So the number of zeros that we have to find matches whatever the highest exponent is. Now those zeros might be all real. Some of them might be repeats of each other. We've talked about that and how that shows up in the graph. We also could end up having imaginary zeros. And those don't have a specific place on the graph, but those can occur, and we can discuss those later. But to find those actual zeros, we have to have some way of narrowing it down. I mean, there's literally infinity places that this graph could be crossing through the x-axis. Same thing with this one here. So we need to have some way of starting to narrow down the possible locations as to where those zeros are. So what we have is the rational zeros test. And so this is going to give us a list of numbers that are possible zeros. Not the zeros, but possible zeros. So we're going to narrow down from infinity possible locations to a much smaller, more manageable list. And so we're going to do that by the following. So we have this formal definition here. Bottom line is we're going to take the factors of the last number, that integer piece at the back end of our polynomial. We're going to call those p. And then we're going to take all of those factors and divide them by the coefficient of the leading coefficient. We're going to call those q. So we're going to call this our p over q list. And so that's how we're going to generate this list of possible rational zeros. So remember, rational is any number that could be written as a fraction. So none of these are, we're not creating a list of possible imaginary zeros or zeros that have square roots in them, but just integers and fractions. And so for our p values here, so for the top, I need all the numbers that divide evenly into 4. And I need both positives and negatives. So I've got plus or minus 4, I've got plus or minus 2, and then I've got plus or minus 1. So those are all of the numbers that divide evenly into 4. And then conveniently enough on this one, for the leading coefficient for my q values, the only thing that divides evenly into 1, because remember there's a 1 in front there, is just plus or minus 1. And so then to create my list, if we scroll down a little bit here, what we can do is we can just start from the biggest negative. So I'm just going to take numbers from the top and divide them by numbers on the bottom. And I want to create the list from the biggest negative to the biggest positive that I possibly can. So the biggest negative I can end up with by taking something from the top over 1 is negative 4. And then I can get negative 2 because I'm just dividing all these top numbers by 1. So I basically just need to list off all the top numbers in order from least to greatest. And then I get negative 1, 1, 2, and 4. And I'm listing them off in least to greatest order just so that I can see them. There are some reasons later that I'll explain that it can be useful to write it this way, but we just want to come up with that list. For the second example, right, so again, the last number, the last coefficient, is going to be our p factors, and then these are going to be our q factors for the 2 this time. So my p over q is going to be all the factors of p of that last number. So I've got plus or minus 9, plus or minus 3, and then plus plus or minus 1. So those are the numbers that divide evenly into 9. And then in the denominator, I put the numbers that divide evenly into 2. So I've got plus or minus 2 and plus or minus 1. So in this one, we're not quite as fortunate by having a 1 in the denominator. We have a 2, so that means we've got more possibilities of how we can divide the top by the bottom. But still, the biggest negative that I can get is going to be negative 9 divided by 1, or positive 9 divided by negative 1. So negative 9 is the biggest number, biggest negative that I can make. Then I can take 9 divided by 2, so I'm going to get negative 9 halves is going to be the next biggest. Then I can get negative 3, negative 3 halves, and then I can get negative 1 and negative 1 half. So I'm basically just taking each of those top numbers and dividing it by the 2 numbers that I have on the bottom. Then I'm just listing them in order from least to greatest. And then it's just going to be the exact opposite order once I get to the positive side. So it's going to be 1 half, 1, 3 halves. Oops, let's try to make that look like a 3 halves. 3, 9 halves, and 9. And so what this rational zeros test does is it takes us, like I said earlier, from an infinite possible list of zeros, infinite number of places where these graphs could cross through the x-axis. And instead now I have it down to just 6 on the first one, which is very manageable. Here we have a little bit more. Looks like we have, what, 12 places, 2, 4, 6, 12 places. So it's still a lot, but it's much, it's way better than having infinite options. So this gives us a place to start to test to see which of these numbers are zeros, as we'll see in the next examples.